Hello everyone, in this session we'll discuss arithmetic circuit. Now all the arithmetic micro operations we had discussed separately, that is binary adder, binary incrementer, binary adder subtractor. So now we want to design such a circuit using which we can combine all these operations and it can be performed using one circuit. So we do not need to implement them separately. So for doing this we require full adders and we'll be putting them in parallel. So we require some parallel adders, and by controlling the input data inputs to this parallel adders we will be getting different arithmetic micro operations, and the formula for implementing that micro operations is depending on d is equals to a plus y plus c in. Now where a is a fixed input but this y is multiplexed input, so based on changing the value of y we would be getting different outputs, so different arithmetic micro operations. Now let's implement the circuit so it would be clear how this y operates and we would be getting different outputs. Okay, so 4-bit arithmetic circuit. For that we require 4 full adders. Now if we want to make n-bit arithmetic circuits, we require n full adders. Over here we are requiring 4 full adder circuits, and as per the design of full adders we require 3 inputs to individual full adders. So the first input, that is x, is given as our a. As you can see, a0 is given to x0, a1 is given to x1, and similarly a2 and a3. So first input for the full adder is defined. Okay, now the second input we are having, that is y, but before discussing y let us go for discussing c0, that is carry input c0. Now carry we are inputting to be c in as per our formula d is equals to a plus y plus c in. A is defined, c in is also defined, and the output of this full adder, that is c1, would be propagated to the next full adder and so on. Furthermore all the carries would be propagated and we would be getting the output carry, that is c out. Now let us discuss for this y, input y. Now y is a multiplexed input, so for that we require multiplexers. A 4x1 multiplexer we are taking. Now 4x1 multiplexer means we require 2 select lines, so S1 and S0. So 2 select lines, and now we are required to give the input to be 4 inputs. So 0th input we are directly providing it to be B. So B0, B1, B2 and B3. Now first line we are giving the input to be complement of B, that is B dash. So complemented, so B0 dash, B1 dash, B2 dash and B3 dash. So the first line input is the complement of B. Then the second line we are providing the value 0, hard-coded value 0. And the third line to the multiplexers we would be connecting it with 1, hard code value 1. So you can see, repeating the inputs again, 0 is connected with B, 1 is connected with B complement, 2 is connected with 0 and 3 is connected with 1. And the output of this multiplexer is given as an input to the full adder input y. So you can see, so from the output of multiplexer it is given as an input to the full adder y0, y1, y2 and y3. And the output of this full adder, which we are terming it to be D, so D0 bit, D1, D2 and D3. So this is our 4-bit arithmetic circuit. Now we are supposed to see the working of it, how it works. So let us take an example. Let us take the value of S1 and S0 to be 1, 0 respectively. So S1 is 1, S0 is 0. So you know the working of multiplexer. So if we discuss about this, then as per this S1 and S0 to be 1, 0, the second line would be selected from the multiplexer, because 1, 0, so corresponding decimal value would be 2, and on the line input 2 we are having value input provided to be 0. So the output from multiplexer would be 0, as you can see. So output from this multiplexer would be 0 over here. But along with that, one more input we need to check out, that is C in, which we have provided to be 1. As you can see, C in is provided to be 1. So as per the formula D equals to A plus Y plus C in, what is the input? How A is fixed, so A plus y. Now y all bits are 0, so 0, so a plus 0, and c in is 1, so a plus 0 plus 1. So can we say it is simply a plus 1? And a plus 1 means it is nothing but our simple increment operation. So the content of a would be incremented by 1, and this is what is our increment micro operation. So using this circuit, by providing the select lines and C in, we can get different operations. Let's discuss one more operation, but before discussing that operation, we need to discuss something, that is decrement operation. Decrement using 2's complement. Now in that case, let us take an example. The number is 1101 and we want to decrement it by 1. So basic binary rules, we are knowing that it would be 1100, so 1 minus 1, so it is 0, and rest bits are 110, so 1100. So this is our normal arithmetic operation. But what we want to do is using 2's complement. So for performing it using 2's complement, we need to take the 2's complement of this bit 1. So this first number remains as it is, and the 2's complement of this 1 becomes 1111, because we are having 4 bits, so we need to arrange them in 4 bits, and we need to take the 2's complement. And 2's complement, you all are knowing, it is 1 complement plus 1. So now after taking 2's complement, we would be performing the addition. So after performing the addition, what it would be? 1 plus 1, so 0, carry 1. 1 plus 0 plus 1, so 0, carry 1. 1 plus 1 plus 1, so 1, carry 1. 1 plus 1 plus 1, so 1 and carry 1. But as per the decrement using 2's complement or subtraction using 2's complement method, if carry is generated, we need to discard that carry. So what with the remaining result is 1100, so which is our normal required decrement operation. Now as per our formula, d equals to a plus y plus c in, if we want to perform decrement operation, what we now give as an input? So a is fixed, so d equals to a, which is fixed. As you can see, d equals to a, which is fixed, plus y should be given as all 4 bits to be 1 from this example. As you can see, 1, 1, 1, 1. So we need to provide all 4 inputs to be 1, and plus over here the carry we have not provided. That means it is to be considered to be 0. So carry C in is 0. So now you are clear about how to implement this in our example. Now 1111y. So that means from all multiplexers we require 1 over here. So which line should be selected from the multiplexer? Line 3, because line 3 gives 1 as an input. So if we want to select line 3 from multiplexer, we need to give input S1 and S0 to be 1, 1. And C in we have decided to be given as 0, so 0. Now as S1 and S0 are 1, 1, our line 1 would be selected, and we would be getting the output Y to be 1 over here. And all 4 bits 1, C in 0, the output of the full adder would be a decrement operation. So the content of A would be decremented by 1. So this is how various operations takes place in this particular 4-bit arithmetic circuits. Now let us list them out. So the arithmetic circuit function says by changing different inputs S1, S0 and C in, we would be getting different Y, and based on the formula D equals to Y, A plus Y plus C in, we would be getting different micro operations. So if it is 0, 0, 0, then Y would be B, and our normal addition operation will take place. So if we provide another combination 0, 0, 1, it would be add with carry. If it is 0, 1, 0, then it would be A plus B dash, so it would be subtract with borrow. If it is 0, 1, 1, so D is equals to A plus B complement plus 1, so it is our normal subtract operation, because we know that for performing subtract operation, A minus B, so we need to take 2's complement of B, so it becomes A plus B complement plus 1, so it is subtract. Then next we can have a transfer operation, then we can have increment operation, then decrement operation, and transfer A again. So this is what is the function table for our 4-bit arithmetic circuit. Now you can also design n-bit arithmetic circuit by using n full adders and n multiplexers. So this is about 4-bit arithmetic circuit.